2 10 marks and module 3 5 marks. So total 30 marks. Right? Okay.
We have one question each, ma'am.
Yes, one question each.
Okay.
Sure. Okay, I'll start now. See, I think yesterday we have seen examples for semi-group. What was the example that we have seen yesterday? Can you please repeat once again? What was the example that we saw? For semi-group, we saw one example, right? What is that example?
Natural numbers.
Natural numbers
Yes.
under addition. Yes, under addition is semi-group. Okay. For monoid?
Whole numbers under addition.
Whole number under addition. Okay. Then for group, set of all integers under addition is a group. Correct?
Yes, ma'am.
Okay. Okay. Even if we have many more examples, set of all 2 by 2 matrices over integers. So what do you mean by over integers? I think you know this concept. If you have studied linear algebra, you know what do you mean by over integers. Nama, what is the meaning of that? M 2 cross 2 over R is a group under matrix addition. So what do you mean by this over R? If you don't answer, that means you have not studied linear algebra. If you have studied linear algebra, you should answer this. Over R means what is the meaning of that?
Under
M2
all
cross
real
2 over
numbers.
R means, huh?
All real numbers.
That's okay. So what is the meaning of here saying M2 cross 2 over R? So how do an element of M2 cross 2 over R look like? A, B, C, D. Such that?
ABCD belongs to real numbers.
That is the meaning of over R here. Right? All the entries from that matrix, all the entries of that particular matrix are coming from real numbers. M2 cross 2 over R is given this way, right? So we have to prove this is a what? Group. So take the closure property. So consider 2 matrices now. So shall we take A1, B1, C1, D1, comma, A2, B2, C2, D2 belong to M2 cross 2 over R. Now, so if you add, when does this addition belongs to M2 cross 2 over R?
When A1 plus A2 also belongs to R, B1 plus B2 also belongs to R, and so on.
Very good, very good. All each of the entry belong to R. So of course you say that those entries belong to R.
Yes, ma'am.
Yes, because A1 is a real number, A2 is a real number. Addition of 2 real numbers is always a real number, right? So this belongs to M2 cross 2 over R as A1 plus A2, comma B1 plus B2, comma C1 plus C2, comma D1 plus D2, all belongs to R, right? Then associative property. Matrix addition is always associative. Even matrix multiplication is also associative. So commutative and associative property, as I told you, it depends upon the operator. So addition and multiplication are commutative and also what? Associative. So automatically you need not verify that. It's very obvious. So you can write matrix addition is associative. Matrix addition is associative. Okay, then identity. Can you say what is the identity for matrix addition? So you need a matrix in such a way that that matrix, whatever you are considering, if it is added with any matrix, that gives you the any matrix, that matrix added again. So what is that matrix?
Zero matrix.
Zero matrix. Okay, so 0, 0, 0, 0 belongs to M2 cross 2 over R is the identity. for any ABCD plus 0, 0 equal to ABCD equal to 0, 0, 0 plus ABCD for all ABCD in M2 cross 2 over. Okay, so you need not mention here ABCD belongs to R, obvious. Whenever you say that, that is coming obviously, right? Inverse. So I need, see, for any matrix ABCD, so for any ABCD in M2 cross 2 over R, I need some matrix such that some matrix, when it is added with this, I should get back what? Identity matrix. So what is that matrix?
1 minus A, 1 minus B, 1 minus C, 1 minus D.
One, why 1? I need 0, 0, 0, 0. So if you add something
Minus A, minus B, minus C, minus D.
yes, comma, minus A, minus B, minus C, minus D belongs to M2 cross 2 over R is the inverse. Okay. ABCD plus minus A, minus B, minus C, minus D is 0, 0, 0, 0, which is minus A, minus B, minus C, minus D plus ABCD. Clear? So therefore, M2 cross 2 over R is a group under matrix addition. Okay. So now please tell me, is this group commutative?
Yes, ma'am.
Commutative means what?
A plus B equal to B plus A.
I should not call group commutative, whether matrix addition is commutative, right? Okay. Now, for, I'll take any two matrices arbitrarily. Very important, arbitrarily. Arbitrarily means what? Randomly you are choosing. That means whenever you choose something random and you prove something, then that is applicable for all because your selection is random, right? Belongs to. Then A1, B1, C1, D1 plus A2, B2, C2, D2 is always equal to A2, B2, C2, D2 plus A1, B1 for all, right? So therefore, what? Which is M2 cross 2 under matrix addition is an abelian group. Not only a group, it is an abelian group. Very important. Is an abelian. This concept is new to you. See, closure, associative, identity, inverse. If these four properties are satisfied, then that particular set is a group under a particular operation, binary operation. So along with that, if the group satisfies the commutative property also, then the group is called abelian group. ABELIAN. Clear?
Yes, ma'am.
Okay, ma'am. Okay. So we'll see more examples. Don't worry. Okay. There are two different, very important concepts here. Two types of groups. Either you can call what? Finite group or infinite group. So whenever you consider a groups, so groups can be classified into two, finite or infinite. Finite means what? If it has finite number of elements in it. So what do you mean by finite number of elements? You know, I think the difference between finite and infinite. So far we have not seen a finite group. We see only a infinite group. One group I have shown you. Z under addition is a group. Okay. Under multiplication, what can be a group? Can you say? Okay, under multiplication. Z under multiplication, will that be a group? Check. Okay, I'll take set of integers under multiplication, usual multiplication, right? So what are the properties that will be satisfied? What are all the properties? Closure. Will that be satisfied?
Yes, ma'am.
I'll take some two integers. Let a comma b belongs to z. Multiplication of two integers is again an integer.
Yes.
Yes. Then a into b belongs to z as a dot b is also an integer. Obvious, right? Associative. What can you say about the associative property?
It also belongs to Z.
It also belongs to Z. If I take three elements, will that satisfy associative property randomly? Of
Yes,
course.
ma'am.
Because just now I told you, operation multiplication is always associative for all. Okay. Identity. I need some element such that A into that element is always A. What is that element?
1 by A.
Illama, I need some element such that A into A is that same A. What is that E? E is
Oh,
the
okay.
identity.
1, 1, 1, 1.
1, 1. So now 1 belongs to Z is the multiplicative identity. Or it is the identity under multiplication, correct? Or 1 into A equal to A into 1 is equal to A for all A in Z. So far, if you have seen Z under multiplication is a monad. Monad, hello? Hello?
Yes, ma'am, it's monoid.
Yes, it is a monad. Any problem is here? Just check. Whatever I said is correct. If you could find some problem, tell me. Closure, okay. Any two integers, if you multiply it is again an integer. Associative property also holds good. Identity also okay. Anything, everything is okay. So what about inverse? What will be the inverse?
1 by A.
Okay. So for every A in Z, comma, 1 by A is the inverse of A. 1 by A is there in A? Is there in Z?
No, ma'am.
No. But 1 by A does not belongs to Z. For all A. Even for 0, it does not belong. Okay. So therefore, Z, comma, usual multiplication is a monoid. So how do you make this a group then? If I take Z, it becomes only a monoid. So under multiplication, so what elements are needed so that it becomes a group? I need multiplicative inverse, right? So what should be added inside Z? Think about it.
Real numbers.
Okay, even smaller than that. Only real numbers. Real numbers, okay.
Rational numbers.
Rational numbers. Okay, rational numbers, you say it forms a group. Okay, what is the inverse of 0?
Infinity or not defined.
Not defined. So you say rational numbers under multiplication forms a group. Think about it. Or something has to be removed from rational numbers.
Ma'am, maybe a rational numbers except 0.
Maybe that is the correct thing. You have to remove 0 from the set of rational numbers, then it forms a group, right? Okay. So Q under multiplication is not a group as 0 belongs to Q, does not have a multiplicative inverse. Q star equal to Q minus 0. They'll write this way or even they'll write this way. Okay, so I'm just removing what? 0 from that. You usually denote it by Q star. Q star non-zero rational numbers. Non-zero rational numbers. So Q star, 1 minute. So Q star is a group under matrix multiplication. Can you please say the things? Shall I write how to prove this? Closure. Let A comma B belongs to, I'll be very fast. Let A comma B belongs to Q star. So A into B, product of two rational numbers is again a rational number.
Yes, ma'am.
It's a rational number, right? Okay. Belongs to Q star. Okay, then associative. A dot B dot C is equal to A dot B dot C for all A, B, C in Q star. Because multiplication is always associative. Identity. 1 belongs to Q star is the identity. Okay. For A into 1 equal to 1 into A equal to A for all A in Q star. Clear? So if you feel that I'm going fast, please tell, I'll make it slow. Then okay, then inverse. Inverse enema for every A in Q star. If you don't like A, you can write it as A by B. Rational number, right? B by A will be the inverse. It's after all a notation, it's up to you. So every A in Q star, comma, 1 by A belongs to Q star is the inverse of A. A into 1 by A equal to 1 by A into A equal to 1 always. Anyway, order you multiply, it is always 1. So therefore, Q star under usual multiplication is a group. Is this a common? Will this be an abelian group?
Yes, ma'am.
Yes, yes. Okay. So we can check the commutative property. Very, very simple commutative. For all A comma B in Q star, A into B is always B into A. So therefore, Q star comma cross is an abelian group.
Excuse me, ma'am.
Yes, ma, tell me.
Ma'am, this abelian holds for only groups, ma'am. Like other things, abelian will not hold.
No,
like
we need not call that as one. See, if for a group, if commutative property is satisfied, then we call that as an abelian group. Okay.
And so then integers under addition will also come under this
Yes,
abelian
of
group.
course, it is an abelian group.
Okay.
Under addition, yes. 1 minute. I didn't write. Oh, group only. If you want, you can. I can add. You can add. I'll write one also. Z comma plus is an abelian group. Clear? I'll include something more. R star comma under multiplication is also an abelian group. Except R star means what? Non-zero real numbers. Non-zero real numbers. That is also an abelian group. Okay, va?
Ma'am.
Yes.
Ma'am, in Q star, can we add all the irrational numbers also and say that it forms a group, like all the fractional numbers except 0?
Sorry, if you add all irrational numbers in Q star, what is that? R star. That is only R
Then it
star.
will become real numbers. Okay, fine.
Rational numbers, real numbers are made up of what? Rational and irrational. So inside
except
rational, you
0,
have
except 0, all other numbers will satisfy. Make
see,
it.
R is made up of two things: rational, irrational. Inside rational, you have integers. Inside integers, whole numbers. Inside whole numbers, natural numbers. Clear?
Okay, ma'am. Thank you.
Jerosha, who asked? Jerosh?
Yes, ma'am.
Okay. And as I told you, there are two types of groups. So before going into two types of groups, the number of elements in the group is called order of the group. The number of elements that is present inside the group is called order of a group. So whenever you take Z under addition, how many elements are there? Hello? Z under addition, how many elements are there? In integers, how many elements are there? Infinite. So it is an infinite group. R under addition, how many elements are there? Infinite. Alright? And Q star under multiplication, infinite. R star under multiplication, infinite. So all these are infinite groups. So far we have never seen a finite group. Okay. I'll tell you some examples for finite groups now. Okay. So first order of a group. What do you mean by order of a group? The number of elements in the group G comma star is called its order and denoted by, like this we usually write. Okay, order. Set order also we write this symbol, right? The same way, order of the group. Okay. So finite and infinite groups. Based on the order, you can classify the groups into two. Finite and infinite groups. So if a group has finitely many elements or finite elements. Oh, I should not say finitely many elements, finite number of elements, right? A group has finite number of elements, comma, then it is called a finite group. Finite group examples I'll give you. So if a group has infinitely many elements, infinitely many elements, then it is called an infinite group. Then it is called an infinite group. Now we'll see examples, right? Examples for infinite group. Examples for infinite group. Z. Usually we write like this, Z under addition. Number 2, Q under addition. Number 3, R under addition. All under addition, all these things are infinite groups. Under multiplication, Q star under multiplication. Then R star under multiplication. All these are infinite groups. Even C star also. C star is complex numbers. Is this okay? Clear? Even C under addition is also set of all complex numbers under addition. C star. We write something like this here for C. We never use normal C. Some bolded something like this. Under multiplication, C star are non-zero complex numbers. All these things are infinite groups. Finite groups we are going to see now. So you need to understand finite groups first, right? Finite groups. Many examples are there. We'll see one by one. First, you need to understand Zn. What is Zn? Right? Zn denotes, it's not usual Z, Zn I'm saying. So the set of all possible values when any integer, positive integer, right? Positive integer is divided by n. What are all the possible values when any number is divided by n? Reminders, possible reminders. You should write possible values and possible reminders. A set of all possible reminders when any integer is divided by n. Can you say what are all the possible values? Nama, when 5 is divided by any number, when any number is divided by 5, what are all the reminders possible?
0 to 4.
0 to 4. So when any number is divided by n, what are the reminders possible?
0 to n minus 1.
That's all. So Zn has 0, 1, 2, 3, etc. n minus 1. Okay. There is one more thing called addition. So I think you understood this. Z5 will have 0, 1, 2, 3, 4. Z6 will have 0, 1, 2, 3, 4, 5. I think you understand what is this Z5, Z6 and all. Clear? This part is clear? Hello?
Yes, ma'am.
General. Okay. Now I want to introduce an operation, addition modulo. Right? Addition operation, addition modulo, addition modulo here. See? For any two, maybe I'll take positive values, any two numbers a comma b, a addition modulo n b is nothing but the remainder obtained when A plus B is divided by N. When A plus B is divided by N. So A addition modulo N, B is nothing but the remainder obtained when you add A and B and divide by N. So that is the meaning of addition modulo N. This operation, have you understood? See, for example, 7 addition modulo 3, 4 is nothing but the remainder obtained when 7 plus 4 equal to 11 is divided by 3. So what will be the remainder? Can you say? 11 when you divide by 3, what is the remainder? Are you all there? I'm speaking alone.
2, ma'am.
Then
2, ma'am.
2. So I think hope you understand what is A addition modulo N B. You have to add A and B and divide by N to get the remainder. So I have introduced two things now, Zn addition modulo N. So always Zn under addition modulo N is a group. I want to prove this. Okay, I'll take some particular example to prove Z5 under addition modulo 5 is a group. Okay. Z5 what are all the elements? I think you know. Z5 has 0, 1, 2, 3, 4. Addition modulo 5 you know. Now, how do you prove this here? We have to prove closure property, associative property, identity property, inverse. But for all the elements you have to prove, because here finitely many elements are there. So closure property, if at all, if you want to prove how many elements you'll take and how many pairs you need to take, because it's a binary operation. Every time you have to take 2 elements and do it. So how many pairs you'll take and do it? Sure, okay. To start with, better, I'll reduce this. I won't take Z5. I'll go with Z3. I'll take Z3 under addition modulo 3. Then I'll go to Z5. Okay. Okay, to prove Z3 is a under addition modulo 3 is a group closure. So what and all elements I can take? Z0 addition modulo 3 1 if you take, that is, what is 0 addition modulo 3 1? No, I think you're not able to understand. 1. So add 0 and 1 and divide by 3 to get the remainder 1. Similarly, I can take the other way. So 1 addition modulo 3 0. So that is also 1. 0 addition modulo 3 2. That is 2. 2 addition modulo 3 0. That is also 2. So 0 with 0, 1 and 2 I have taken now with 1 addition modulo 3 2. What is 1 addition modulo 3 2?
0.
0.
Huh?
0.
0. Similarly, 2 addition modulo 3 1 is also 0. Something is still missing. Have you taken all possibilities? No. I can take 0 with 0 also, right? That is 0. Then 1 with 1 also I can take 2. 2 with 2 also I can take. That is 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 possibilities. Right? And all the 9 possibilities true. So closure property is satisfied. So Z3. How do I say it is closed? Because all the resultant elements, whatever you are getting, are all elements of what? Z3 only, right? Hello? You want every time you can write belongs to Z3. 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 So therefore Z3 under addition modulo 3 is closed. Try to understand this. Clear, huh? Hello?
Yes,
I should consider each
Yes,
and
ma'am.
every pair. Since it is finite, every pair I said it is closed. Now, associative. Associative you can write directly here. It is after all addition, right? Even though addition modulo you are going to add. So, A addition modulo 3B, the resultant addition modulo 3C is always equal to A addition modulo 3, B addition modulo 3C for all ABC in Z3. So Z3 is associative because operation is itself associative. Identity. So what is the identity element here?
0.
0. So Z3 has 0, 1, 2. Yeah. 0 belongs to Z3 is the identity for any A belongs to Z3 if you take any element. Here there are only 2 elements, right? Take 1. 1 plus 0, this is also 1. And 0 plus 3, 1 is also 1. Similarly, 2 addition modulo 3, 0, 2. 0 addition modulo 3 is also. We are getting back the same element. So 0 is the identity. Inverse. Inverse of 0 is what? With 0, what you add, you'll get 0 back again. If you add something with 0, I need something like this. 0 addition modulo 3 something so that I get back 0. So what is that element that you need?
0.
0.
0. Any order you add, you'll get same thing only. So 0 is the inverse of 0, self inverse, right? Okay, inverse of 1. What is the inverse of 1? 1 addition modulo 3. What is 0?
-1.
Here there is no -1, right? You have only 0, 1, 2 in the group. You know inverse of 0 is 0. Just remove that. Inverse of 1 should be what? If you add 1 with something,
2, ma'am.
what is
2, ma'am.
2? 1 addition modulo 3, 2. How do you do that? First you add 1 and 2. 3 you'll get. So what is a reminder? When you divide 3 by 3, 0. The other way also, if you add the, you will get the same thing. Correct? Got it? So inverse of 1 is 2 and 2 is 1. Correct? Both are self-inverse. Inverse of each other. So therefore, Z3 under addition modulo 3 is a group. Okay, is it abelian? Yes, of course. Here itself you can say it is abelian. You are adding in any order, you are getting back the same. Also, A addition modulo 3B is B addition modulo 3A for all A comma B in Z3. So Z3 under addition modulo 3 is a abelian group. It's an abelian group. Clear?
Can you show the previous slide, ma'am?
Yes, ma'am. Yes. Need not put this. Simply you can write Z3. Directly also you can write like this itself. You need not put this.
Can you show the identity slide?
Yes. What happened to that? Here it is. Okay, va? Hello?
Yes, ma'am.
Okay, ma. See here. See for Z3 under addition modulo 3 for closure, how many pairs we took? 9 pairs, right? Okay. So, but if you go for Z5, you need 25 pairs. So to avoid that, you can form a table like this. This is called a KLA table. KLA is a mathematician. It's called KLA table. What you can do is, I write all the elements here. Column headings 0, 1, 2, 3, 4. Here also I'm writing, and this is the operation. I'll do one thing better. I'll form a table and show it to you. Don't worry, I'll take only 5 minutes. I can understand time is not there. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Addition modulo 5. That means by the way of forming this table, I'm going to complete everything. So 0 addition modulo 5, 0. 0 addition modulo 5. What is this value? 0 addition modulo 5, 1. This value 0 addition modulo 5, 2. So that way all 25 entries will come here. Closure property can everything you can see this table and say directly, right? Okay. 0 addition modulo 5, 0, 0. What is this value? 0 addition modulo 5, 1. 0 addition modulo 5, 1. That is this value. What is this? You have to add 0 and 1 and divide by 5. What is the answer?
1, 2, 3, 4, ma'am.
Directly 1, 2, 3, 4. Okay, go to the second row then. 1 addition modulo 5, 0. 1. 1 addition modulo 5, 1, 2. 1 addition modulo 5, 2. What is that? 3. 1 addition modulo 5, 3 is 4. 1 addition modulo 5, 4. What is this value?
0.
0. So shall we complete this directly? Shall I write 2, 3, 4, 0, 1. So 3, 4, 0, 1, 2. 4, 0, 1, 2, 3. So how many all these entries are obtained as the closure operation, right? Operation you have performed. So 25 entries are there. If you look into all the 25 entries, all these 25 entries are elements of what? Z5 itself.
Yes, ma'am.
So that shows that Z5 is closed. If you take any two entry from Z5 and perform addition modulo 5, it is there inside Z5. All these entries are obtained as performing closure operation, right? So that the group is that particular set is closed. The same thing here I have done. Okay, sorry. Associative property you can write directly. Addition is associative. So what could be the identity? Can you just observe this and say what will be the identity? Every element, if it is added with some element, it gives you the same element. So what is that element that needs to be added with every element?
0.
0 is the additive identity. Okay. So what is the inverse of 1? If you add something with 1, you should get 0. What is that? See
Minus
along.
1.
Let's see along row 1.
4,
1
4,
added with
4.
4. 1 added with 4 is 0.
So 5 minus 8 is the thing.
So 1 addition modulo 5, 4 is 0. Similarly, 4 addition modulo 1 is also 0. So both ways it is 0. So inverse of 4 is 1 and inverse of 1 is 4. So what is inverse of 2?
3.
3.
3. That's all. Everything is mentioned here. So Z5 under addition modulo 5 is a group. Okay, I'll stop here. I think your class time is over. So most probably